And if any of you saw my ICM talk on this subject, you'll see I've plagiarized quite heavily from that. There will be a lot of overlap. However, with a much more intimate audience and possibly more aggressive questioning.
Can you plagiarize from yourself? My daughter asked me that. Can you?
I think you technically can, yeah.
Okay.
So, so if you go online here and look at my webpage, you can see I have here the talk. You can see me giving the talk wearing a tie even. And I have lecture notes, which have a lot more information about this. Okay, let's get back to the talk itself. So, the story I start with is imagine a student asks you, what is the canonical random path? And everyone here would have a good answer for that. There's one random path that's more special than all the others, Brownian motion. You'd say, well, consider the random path on Z where at each step you toss a coin to see whether you go up one or down one. And you have a sequence of coin tosses, and you just draw a graph like this, and then you take a limit where you scale by C in this direction and root C in this direction, and the path you get in the limit is Brownian motion. And students say, well, great, but can you define it directly in the continuum? And you would say, sure, just fix a set of points and make the increments independent Gaussians where the variance is the time change, and that tells you how to define it on a countable dense set and extend it to all time by Kolmogorov-Tensov. This is what you would do if you were taking a graduate course in probability. So one of the first lectures, you would just kind of work through this carefully. That's defining Brownian motion. And I said you can define it also in terms of it's the only random path with certain symmetries, and it's universal in that it's the limit of all kinds of discrete walks that you can define. And if you want a random path embedded in RD, you could just say, well, just take a vector B1 through BD where each of these is an independent one-dimensional Brownian motion. And so, for example, here's two dimension. This is a Brownian motion run for a fixed time. And I condition it to come back to where it started at the end. So it made like a Brownian loop. And this is what these things look like. This case too is special because there are a lot of nice theorems about it. For example, Lawler, Schramm, and Werner proved Mandelbrot's conjecture, which says that the outer boundary of this loop is a random fractal curve with fractal dimension 4/3. Right? It's one of these so-called SLE curves. Okay, so that's random paths, just overview. But now imagine the student asks you about random surfaces. What's the canonical random surface? And the instructor would say, well, you're just going to take a bunch of triangles, say, here's some triangles, and I'll glue them together along their edges. So every edge I'll make a partner, and I'll just take some glue and glue the two edges. And so if I started with, say, 30,000 triangles, as in this picture, then that means I have 90,000 edges. And like, how many ways are there to assign every edge a partner and glue it in an orientation preserving way? Well, it's, I don't know. It's what, 90,000 double factorial or something. There's some name for it. It's kind of a simple expression. There's some way of doing this. And sometimes if you do it, you won't get a connected surface, but suppose we condition on getting a single connected surface and having it be like simply connected. So not a torus or something. And so if I condition on that, take uniform among all the things that give me this, I get a random sphere homeomorphic surface, just made by gluing triangles together. And what you say is if you take the n goes to infinity limit, you get a random surface called the Brownian sphere. And it's also called a piano sphere or Liouville quantum gravity sphere or a conformal field theory. The student complains, well, you just listed 4 things. Which one actually refers to this? And the crux of the talk is, and actually, all of these different items are different ways of defining the same random surface. Say if you have 4 blind mathematicians feeling the surface of an elephant, they would describe it in these 4 ways. And what those things are specifically, the Brownian sphere is a way of constructing a random metric measure space So it's a metric space, has the notion of distance. I give you 2 points on the surface, you can tell me how far apart they are. The pianosphere is a way of constructing a surface by gluing together a pair of trees along their boundaries in a way that oddly creates a topological sphere where the interface between the two trees becomes like a space-filling curve, a piano curve. So they call that as pianosphere, if you try to understand its trees. There's something called the Liouville quantum gravity sphere, which is something that has a random conformal structure. It's sort of a random Riemannian surface in a sense. And there's what we call conformal field theory, which at least from this point of view is a way of making sense of kind of multi-point functions. So I'll say more about that later, exactly what this means. Okay, so a quick kind of technical point. Usually when we think of a unit area Brownian sphere, we think of it as like a sample, like a measure ds on the space of all unit area sphere homeomorphic surfaces. But there's also sometimes a variant you want to discuss called the unrestricted area sphere. And that's where you allow the area of the surface to also be random. And so it turns out if you have k marked points on your surface, the natural measure is, we take a to the minus 7/2 plus k dA. This is a measure on the real numbers, an infinite measure on the real numbers. And then given the area, you choose a surface of that area, uniformly among surfaces of that area somehow. And this is something that just comes up in the discrete models. Like if I want to count how many ways are there to actually glue those triangles together to make a sphere, it turns out that it grows somehow exponentially in the number of triangles. Well, it's exponentially some beta to the n, where n is the number of triangles times some constant. And there's like a polynomial correction factor. And that factor is n to the minus 7/2 plus the number of distinguished points. And so when you take a limit, it's kind of natural to preserve this. Imagine you have a continuum surface where the area itself is random. That's just something that comes up. All right. And another thing they sometimes do is say, well, what if you replace beta, this weight, instead of, if you weight the counting measure by beta to the minus n, then that would kind of cancel this thing. And you'd get something whose limit would be this continuum measure. But sometimes they say, what if you weight instead by beta to the 1 plus epsilon mu, where epsilon scales to 0 in the right way. And it turns out if you do that, you get sort of a variant in the continuum, where instead of weighting by just this thing times dA, you also weight by e to the minus mu a, where mu is like a constant times the total area. So anyway, I don't want to dwell on that too much, but just say there's a variant of this where you kind of weight by the total area to keep the area from getting too large. And this came up in Poyakov's early work on this subject, because he was thinking of these things as two-dimensional models for gravity. And this mu is formally the cosmological constant of Einstein's equation in that perspective. But if you don't care about that at all, and you just care about statistical physics of random surfaces, you would just say, well, I'm just taking this beta to be slightly off critical, and it's giving me a slightly different kind of limiting function. All right. So if you want to describe a random surface embedded in RD, what you do is you weight the random surface by the number of, you weight the law of your original surface by the number of ways to embed it in RD. So
by the way, in your ICM talk, I assume since it was given at MIT, this was a student and the instructor at MIT. This is not the normal discussion of a student.
This is a high quality student. Instructors who are very quick on their toes. Yes. All right. So, so, if you basically, you kind of want to take your probability measure on random surface and imagine you get a surface together with an embedding of the surface in higher dimensional space. So the marginal law on the surface itself, this discrete graph, would be the somehow you'd weight each graph by the number of ways to embed it in higher dimensions. And number of ways might be like the partition function of what we call a Gaussian free field on the planar map. So it's some sort of continuum way of counting the number of embeddings. Maybe I'll leave it at that for now. And it turns out the higher the dimension of the surface you're embedding these in, the rougher the surfaces get as metric spaces. So, and if you're sort of weighting by this partition function to the d's power, you can make sense of that for any d. It doesn't even have to be a real number. And it turns out that these things converge to the Euclidean sphere when d goes to minus infinity, and they become random metric spaces for any d up to 25. That's his famous sort of bosonic string theory threshold. Okay, so let's get back. So let's take a deep breath and go back to something a little more concrete. Here's a random graph, or just even a graph. So a planar map is a finite graph embedded in the plane, where two embeddings are equivalent if there's an orientation preserving homeomorphism of the extended plane that takes one to the other. So these figures here, they're isomorphic graphs, but they're not the same as planar maps because there's no way to deform the plane that takes this point from being in the middle of the square and moving it to being in the middle of the triangle. All right. Now, combinatorially, this thing is determined if I just give you the graph together with a clockwork bicyclic ordering of the edges around every vertex. Sometimes to eliminate the ambiguity from non-trivial automorphism, you will specify a root, specifying a specific oriented edge. If I were to give you a map, say, of South America, you can draw a vertex in the center of each country and an edge between countries when they share a non-trivial border. So this is sort of like the dual map of a physical map of countries you might see. The famous four-color conjecture says that there's always a way to color the vertices of a planar map in such a way that no two adjacent vertices have the same color. And this was famously first posed in 1852 and then solved in a computer-assisted proof in 1976. And Tutt made important progress in the 1960s. So anyone thinking about planar graphs in that era would have had certainly this problem in their mind. And that's what he was interested in solving. And he started by saying, what if we just count the total number of rooted planar maps with edges? Let's just enumerate them all. And he came up with his lovely formula. This is the number of them. So this weird thing has this exponential factor, this 3 to the n, and it has this other part, this kind of polynomial in it. Asymptotically, it's this c in constant times beta to the n times this polynomial correction factor, where here beta is 12, k is 1 because there's sort of one marked point on the planar map, and we'll see it's just some constant in Stirling's formula. And so triangulation is the case, what we call a planar map in which all the faces are triangles. Quadrangulation is what we call a planar map in which all the faces are quadrilaterals. So you can come up with different similar formulas for counting those. So now that you have a method of counting them, you might ask, well, what if I just enumerate them all, list them out, and choose one uniformly at random from the set of this many possible surfaces? And so here's a lovely picture of that by Budzinski, what I showed at the beginning with the 30,000 triangles. And he took this thing and embedded this thing in three-dimensional space. And so if you just use Mathematica or some other software that deals with displaying graphs, you can plug in the graph and say, embed it with a spring embedding. And what it does then is it imagines that every vertex is an electron. Every spring is a spring obeying Hooke's law. And so the forces push the electrons apart. So that they repel each other, but then the springs hold them together and keep them from getting too far apart. So it naturally inflates into this shape in 3 dimensions, and you can kind of see it has a surface. So in order to make this, I didn't have to tell the computer that this was going to be a surface. I just put in this thing as a graph, and it just inflates it out with these electric repulsive charges. It forces it out into being this surface. But you can also try to think, what other structure is there in this kind of random graph. So the Brownian sphere is what you get when you kind of interpret this thing as a what we call a metric measure space. So between any 2 points, there's a distance, which is the minimal number of edges you traverse to get from one point to the other. And if you kind of take a limit, you can show that that distance converges to something in the limit when you scale the right way, and you get a random surface. So when you take limit in a certain topology, Gromov-Hausdorff-Prokhorov topology, if you don't know what that means, it doesn't matter. It's just a way of putting a metric on a set of measuring down surfaces. So if you take a limit in this sense, you kind of get a random metric measure space. So these authors here, parentheses, were instrumental in showing that this thing really makes sense mathematically. Here's some other, this, I think if I click this, it'll pull up a few of these other guys. Here's another picture of this random map by Benedict Stuffler. Much more artistically impressive than my own pictures. And you can see there's a lot of fractal structure to these things. There's self-similarity. And he actually drew this picture in a way to give us a hint of the metric space structure. And the way he did it is he colored every vertex by the distance between that vertex to the average distance to all the other vertices. So the ones in orange are essential. If you had to visit every other vertex once a month, you were the post office person, you would rather live in the orange areas because you're central. Whereas here, the average distance on the periphery is far from everywhere else. And so looking at this, you could kind of feel like, there's no way I can display the distance between every pair of points. But you kind of feel like you get a sense for the metric space structure of this surface from something like this. Okay. Let's go back to here. Now, another way of looking at this is as a mating of trees. So both the Brownian sphere and piano sphere can be defined in the continuum as matings of random fractal trees. So before we get into that, let me mention Julia sets. So K is a set of points that remain bounded under repeated applications of phi z equals z squared plus c. That's a Julia set. Different values of c give you different crazy fractal looking shapes like this. Phi is going to fix a set K, and phi will be a 2-to-1 conformal map from the complement of K to itself, which, and there's, if I take the phi preimage of a small blob that intersects one of these little things, it will be 2 small blobs, the preimage that's 4 small blobs, etc. And that kind of counts for the lovely self-similarity. So probably won't spend much, I think most of you have probably seen these things before at some point in your lives. But maybe what not everyone has seen is that there's a way of gluing 2 Julia sets together along their boundaries. So if I take a Julia set like this one on the right, I could take a conformal map from the complement of the red set to the complement of the unit disk. Then the uniform measure on the unit disk, when I pull it back here, would induce a measure on the outer boundary of this curve. It's sort of like if I did a random walk coming from infinity, it's sort of the probability distribution of where that walk would hit. But it's a natural measure. If I give you another Julia set with a measure on that, and suppose I glue the boundaries together in a boundary length preserving way. That gives me sort of a new weird surface, some sort of concoction by gluing these things together. And then I try to conformally map that into the sphere and get a sphere with 2 things glued together. Well, you can't possibly visualize what I'm saying, but someone else made a wonderful picture of it. So Arnaud Cherrytop, if you go here, he has a wonderful website with a lot of things, and I'll show you one of his wonderful pictures. So here is gluing together 2 Julia sets.
Are they Julia sets of one rational map, or?
I think in this case, it's the same C,
Okay.
but it doesn't have to be the same C.
But it's a quadratic.
But it's just a quadratic. I mean, I think they can maybe do some other cases, but in this case, they're all just a quadratic. So very simple. Okay, but it turns out that the Julia set structure is very rich. So depending on what value for C you get different types of Julia sets. So this is the same thing, but with a different value of C. In this case, the Julia sets are trees. So let me just go back to the beginning here. they're dendritic. This Julia set has empty interior. And so when I glue together two things of empty interior, you might think, how can that possibly make a sphere? But you can kind of see what happens as you glue these things together. They sort of snake in. And if you took this way sort of all the way to the end, you'll get two trees filling up a sphere. And in between the two trees, there'll be a space-filling curve that snakes in between the two trees. One of these lovely space-filling continuous curves that doesn't cross itself, but it does hit itself as it comes back. And you'll have these kind of two space-filling trees that sort of intertwine between each other. Okay, so this was discovered in the 80s. And so, there are lots of different kinds of Julia sets, and any of them you can try gluing together in this way. And this is just to show that, you can draw this Julia set with, say, these are 3 lines of Mathematica code. It's very easy to kind of produce these things. Now, if a student asks you what's the continuum canonical random tree, you would probably say something like this. Well, start with a, I'm going to draw this up on the board. Need to use the board in this talk some. So I toss a coin and I up, down, and I make some sort of path, let's say that's conditioned to come back to the origin after n steps and stay non-negative in between. And I can actually use this to make a tree. And the way I do it is I just glue together any two edges if there is a chord under the graph that connects them. And then I do this and suddenly I have this. So this gets squashed to an edge, this gets squashed to an edge, this gets squashed to an edge, and then like 1, 2, 3, 4 things on top of it. Okay, and you can see you could go backwards. If I gave you this picture, you say, well, here's the root. Keep track of my distance from the root as I go. It goes up 1, down 1, up 1, down 1, up 1, up again, down, up, so as I trace the boundary of this, my distance from the root follows this graph here. So, and you can take a continuum limit where you use what we call a Brownian excursion, Brownian motion condition to stay positive, come back to the origin at the end, and you get what's called the continuum random tree. Okay, so all this, as far as I know, was the first to formally describe this continuum construction in '93, although the discrete trees, as far as I know, have been folklore forever. I don't know who would have first described that. So a student says, is there a discrete analog of this? He says, yes. Consider a tree embedded with n edges. That's this version here. And so that's a bijection between n vertex rooted planar trees and simple walks on Z plus with 2 n steps starting and ending at 0. All right. And so that's all the Brownian tree is. It's just this, it's sort of the limiting uniformly random planar tree of a given size. And it sort of comes with an embedding in the plane, like it's up to diffeomorphism of the plane. Okay, so now I ask, what if I try to glue 2 of these random trees together? So here I take a Brownian excursion xt and a constant minus yt. Yt is a different Brownian excursion. And I make the constant big enough so these pictures don't overlap. I glue these 2 things together and I make these 2 trees here on the right. And now I'm going to draw vertical lines. So I'm going to identify points on the top tree with points on the bottom tree according to these lines. So I'll consider them equivalent. And so you can imagine that's what's going on with these arrows. These 2 trees are being glued together, as in that Julia set picture I showed. And the resulting structure becomes a sphere with a space-filling path, and we call that a piano sphere. Okay, and depending on what type of, if you make these 2 Brownian motions correlated to different extents, you can actually change the nature of the sphere you get after you glue these things together. Now, let me first say that the fact that you get a topological sphere can be deduced by a theorem due to Moore in 1925, where he said, when is it the case that if you take so it's clear that this thing is a sphere if you just take the outermost rectangle and identify that with a point. So you kind of start out with that sphere. He says, well, if you take a sphere and add a bunch of other equivalence relations, when is the quotient by those a sphere? And there's kind of a very simple set of criteria for that. And you can actually just verify those by hand in this set. It takes a little bit of work. but you can actually check that you get a sphere when you glue together these Brownian trees. And and the fact that the correlation of the trees matters, I like to show this with kind of my hands. If you think of this hand as a tree, and this hand as another tree, they're very correlated with each other. They're very similar, these two hands. If I glue the two hands together, put one on top and I glue them together like this, I just get essentially the same tree back because they were equivalent. So you glue together two identical trees, you just get the same tree track back. But if I take my hand and I shift it over by a slight amount, my hand is negatively correlated with the shift of my hand. And now when I glue this thing together, I get something that looks much more like a sphere with a space-filling path that goes kind of back and forth a lot. So this is sphere-like, this is tree-like. And so as you adjust the correlation coefficient between these two trees, you move between more tree-like random surfaces and more sphere-like random surfaces. There a question?
Yes, I'm not sure. How do we should think of how does the curve provide the geometry or metric on the sphere, or whatever it is that it provides?
Yeah, well, that takes some work. So, a priori, when you glue these things together, what do you have? Well, you do have a notion of length in that these trees came with the notion of length, in that you can see to get from here to here, I have to go down some units and then up some units. And that gives me a natural way of describing a metric on the tree itself. It's sort of the limit of the natural metric on the discrete trees. So I have a metric structure on these two trees. And you might think, does that determine for you a metric structure on the overall object? Well, it's not so obvious. Does it tell you how to conformally embed this thing in the sphere? Well, that's not so obvious either. It took us years to figure out how to actually prove that this pair of trees uniquely determines a conformal structure. And there's a metric on that, so various people have worked on this, and this was a major project. So it's not obvious, but it can be done.
How do you go from a conformal structure to a metric? Is there some special metric?
Yeah. So what happens is you get a conformal structure. Well, I don't know, maybe I'll go a little further in the talk before I answer that question. So we talked about these Liouville surfaces. That's where you see the conformal structure for free. We construct the metric from those. Okay, so here, here's an example. A quadrangulation with a planar map. So the thing on the right here, I'm just taking any old planar map in black with blue vertices. And then I'm putting a red dot for each of the dual vertices. Then I go over here on the right and I draw a green line connecting each of the red dot to all of the blue dots in the face around it. Counted with multiplicity as you trace the boundary of the face. So for every black edge then becomes the center of a quadrilateral, kind of 4 green edges around the outside. Well, this one's sort of degenerate. 1, 2, 3, but still 4 edges if you count as you trace around the boundary. So I have all these quadrilaterals glued together. And if I were to take all these black edges and rotate them 90 degrees, I would get this dual graph, which is this dotted line. And so there's a discrete version of this mating of trees, which says I kind of, basically I start with a walk in Z2, starting ending at the origin. And I end up producing a pair of trees like this one over here. So I just take the walk X sub n and the walk Y sub n, and I graph them this way, and I draw these vertical red lines, and I glue the top thing together and the bottom thing together. I get these two trees with these red lines between them. If you think about it, this is a triangulation, because for each one of these a walk in Z2 at every step, it either changes the X coordinate or it changes the Y coordinate. Which means I go from here to here, either this one is flat and the top one changes, or this one changes and the top one is flat. Because if I glue together all the flat ones, then what happens is that all of these things become triangles. And so this thing here is a gluing together of triangles together with this kind of pair of, well, there's sort of a pair of trees that, as you go through here, this is sort of like a space-filling path that visits the triangles one at a time. And then on either side of that space filling path, you have these two trees. And you can kind of see that you can sort of construct the quadrangulation Q on this information. So Q is bipartite. Blue and green vertices are the two classes. Each quadrilateral has one blue to blue diagonal, and they form a planar map M. And then there's a dual map M star. And so there's this bijection between simple walks in Z plus that start at the origin on one hand, and pairs MT, where M is a rooted planar map and T is a spanning tree of that map. So basically all I'm saying is that if I give you the pair X and Y n, you can reconstruct this picture up here. And if I give you this picture up here, which is this planar map with this tree and this dual tree, you could kind of go back and reconstruct a picture like this. So let me show you. Okay. Yeah. All right. And if you think about what's happening here, I'm not just choosing a random planar map, I'm choosing a planar map with a tree on it. So the probability of a given map in this model is going to be the number proportional to the number of spanning trees that map has. All right, so probability measured on n-edge maps, where the probability of a map is proportional to the number of spanning trees. So there's a Kirchhoff's matrix tree theorem says the number of spanning trees of M is a form of the Laplacian determinant of the Laplacian of M.
That star.
That star, yeah, technically right, because you want to ignore the
zero
node. Right, that's right. The constant functions. So the partition function of a Gaussian free field on M is the same determinant, or det star if you prefer, to the -1/2 power, it turns out. And so this kind of says if you want to describe the number of ways of embedding a planar map in n-dimensional space, it's basically this determinant to the -n/2 power. And so and so somehow I could say in this case, put it this way, a tree-weighted random service is kind of like a random service embedded in RD with D equals -2. You're weighting by the number of real embeddings to the -2 power. And something natural about this thing is it's sort of saying, if I give you a planar map and ask you how many trees it has, if the map itself is just a tree, then it has only one spanning tree. And so our intuition is like, the more tree-like your map is, the fewer spanning trees it has. So when I weight by the number of spanning trees, I'm trying to make it less tree-like. So the thing that is decorated by a spanning tree will be less tree-like than the original. And so you kind of think of it, this parameter D as just being something you can tune, where when D gets all the way, when D gets up to, I guess 1, it starts to look a little more closer to being a tree. And then once it gets above 1, it starts to really look tree-like. And when it gets all the way down to -infinity, it starts to look less and less like a tree until it eventually looks like a sphere. So that's the intuition here that's going on. All right. I just want to remark there's also an unconstrained variant to the Moulin bijection where you relax the restriction that xn is non-negative, and then you'll get, but you still get a pair of trees, and you'll just get a different kind of march point. I just point this out because that's the one I used to make this picture. But here you take a 2D random walk on C2 starting and ending at the origin. That gives you a pair of paths. You draw the vertical lines, horizontal lines under this wrapping around if you need to create a pair of trees. And you glue those trees together. So here, this is the walk in Z2, starting at the origin. This is the same thing I showed at the very beginning if you take the continuum limit, this Brownian loop. you take this natural Brownian loop and say, hey, instead of constructing an SLE curve by looking at the outer boundary, let's take the same Brownian loop and use it to produce a completely different structure. So that Mandelbrot did not consider. And this one is, we just take the pair of trees and we glue them together and we make something. And this, by way these lines here, I'm just showing that this is just the Mathematica code to produce this thing. It's probably not the best way to write Mathematica code to squeeze it all into 3 lines with no comments, but at least it illustrates the fact that it doesn't take a lot of code to produce these pictures. They're kind of very simple things to describe. Okay, so here a little more code. I make the corresponding pair of trees. And this again, this uses the spring embedding, but it restricted to the plane. And it sort of embeds the tree, so you can kind of see the tree-like structure. Maybe I'll zoom in a little. Oh, okay. No, that was a disaster. Can you remind me on Zoom? All right, okay. Anyway, so you get this idea. These are tree-like things. And then I can add those red edges, and which is a couple more lines of Mathematica code. I conformally map. I use the spring embedding, and I get something that looks very much like a 3-dimensional surface. Here's one using just the edges. And if I type this other one line here, this, and by the way, you can get all this code on my website. The slides that are there contain the same code and also the ICM notes have this code. So if you want to play around with these figures, they're kind of very, you just plug the code in and it will do this for you. But here, the rotation, let me show you what that looks like. So that code, the colored version, spins it around, it gives you a surface like this. And the version without the colors gives you something like this. Some sort of, I don't know, ice skating animal of some kind, spinning around. And again, the nice thing is I don't have to tell it to make it look like a surface, just the natural spring embedding inflates it into this shape, and you can clearly see the 2-dimensional structure of this object. Okay. Now, I can change this correlation parameter, making things more or less correlated, as I mentioned earlier. And it turns out, though it's not all obvious, that changing this rho parameter is equivalent to changing this d parameter in some sense.
What was the rho parameter?
So rho is just how correlated. There's a correlation coefficient rho that tells you how correlated these 2 Brownian motions are. So it's something between 1 and -1. And as that correlation coefficient goes from -1 to 1, this dimension parameter goes from -infinity up to 1. So it's a way of kind of parameterizing surfaces from more to less rough. And so intuition, highly correlated Brownian trees are rougher, more tree-like surfaces. Highly anti-correlated Brownian trees are smoother, more sphere-like surfaces. So here, for example, Jeremy Brettinelli did a bipolar orientation decorated planar map, which in some sense corresponds to d equals -7 in the scaling limit. And if we click on this link here, I think it will pull up his lovely website where you can actually click on these things and zoom out and in, let me get the right amount, and spin them around. And this is a surface which you can see looks considerably smoother than those Brownian map surfaces. So a dimension, by the time you get to -7, I mean, it's still a fractal surface. If I put too many edges, it would be hard to draw the picture this nicely, but it's a much smoother kind of surface. Here's one of Stouffer's nice pictures, which is 8M, which is also kind of a dimension well below 0. And you kind of see this is much, even with a huge number of vertices, it looks much smoother than his Brownian map picture, which was this one here. Okay, so that's this kind of parameter between how wild you want your surface to be. Now in, what they call bosonic string theory, you're imagining that you have a string tracing out a surface in 4-dimensional space or some dimensional space, over time. So the time trajectory of a string is a surface in space-time. And so, somehow the dimension of the surface is the dimension of your space-time in that telling of the story. And that's the, okay. So let me now talk to Brownian spheres. We want to define this Brownian sphere formally. It turns out that there's a different bijection. I won't describe it in detail here, but it's you start with this Molen bijection with this pair of trees, and you kind of put a little bit of a twist in it. So instead of just drawing horizontal lines, you draw a line that starts on the right and then goes down 1 unit when it crosses here. So you get a slightly different thing. And when you do it that way, this green thing becomes a tree. And now, when I do the gluing together, it's going to be a little bit different. So I'm going to kind of, I'll take the green tree and I want to condition on it being the case that I can kind of glue the top thing together to make a tree. And so the top thing, so I make this blue tree over here. I want to say that if I have any 2 points here that correspond to the same vertex or that sort of map to the same point on the blue tree up here, then they have to, how should I say this? I want to say that if I follow like a pie shape here, I start this thing, I follow the red line up, blue line over, red line down, that I always come back to another vertex of the same height. Like a weird constraint. I'm no longer choosing uniformly random pair of paths. I have this weird constraint that these pie-shaped things always have their 2 legs being the same length. And if you put in that weird constraint, then it turns out that when you shrink these things together, you get this random surface. And then when you delete all of these blue lines, you get a quadrangulation, which turns out to be uniform among the set of all quadrangulations. And these numbers on the blues tells you the distance to the root. So this green tree turns out to be a tree of geodesics. So it's kind of morally like taking the 2 trees, but conditioning one of them to be a geodesic tree to the root. But there's some combinatorial details. You'd have to stare at this for a while to really make peace with it. But it's a relatively simple bijection, which is essentially just 2 span trees, condition one of them to be a geodesic tree in it. And you get sort of a uniform measure on quadrangulations. So this is what they use when they were describing the Brownian map. And it turns out that if you take this picture here and you imagine that you trace the outer bound, this is like a labeled tree. So this blue tree up here, all the places have numbers. There's 1, 2, 3, 4, and the numbers corresponding to the height of the green vertex at the other end of the line. So at the top, I have a tree with labels, and it turns out that there's a 1-to-1 correspondence between these guys and just these labeled trees, where the label just changes by 1 or -1 or 0 as I go from one edge to another, and they stay positive, and they're one at the bottom. And there's kind of a way of understanding these labeled trees where you say, as I trace the boundary of a tree, I always keep track of the path back to the root. So, if I give you a tree, let me just draw for you a tree here. And you're tracing the boundary of the tree. Maybe I can even use this tree. What is that? I trace boundary. If I get to this point on the tree here, and you ask, where are you on the tree right now? You can say, well, I'm at the point where the path to the root looks like this. And you can tell me what the whole path to the root is from your tree. And as you move around the tree, that path to the root changes. And if it's a labeled path to the root, you can kind of draw a curve that tells you how how the labels go, -1, 1. So if label goes down, I go left, it goes up, I go right. And this is sort of like a graph of the label, maybe rotated 90 degrees, but it's, and so I would get this graph corresponding to this single path. And as I move around the tree, this path will be sort of dancing around. And the way it looks like is like this, is you have kind of a what we call a snake, where it can either go up at any stage, and then when it goes up, it can go up left, up right, or straight up, or it can go down. If it goes down, you just delete the edge on the top, move the head down. Okay, so that's what the snake is doing. And if you take the scaling limit of this snake, then there's going to be like a continuum thing that we call the Brownian snake. This came from Liouville in the 1990s. And it's basically just the vertical coordinate is just doing a Brownian motion. But at any given point, the left-right correspondence is sort of like doing a separate Brownian motion whose time parameter is the height I've given up to this point. It's just doing a Brownian motion indexed by the tree, I guess. But if I take this coordinate, the x coordinate and the y coordinate of the head of the snake, those are two processes. I use those two processes to make a pair of trees, like I did before with x, t, y. I glue those trees together, and then I get the Brownian map. Okay, so that's the Brownian map. It was actually a little trickier to describe a random surface decorated by or without a spanning tree on it than a random surface with a spanning tree. If I want it with a spanning tree, I just take these two independent trees and glue them together. Here, well, I have to take a slightly more complicated off of it, this Brownian snake creature. But in the end, I still just get two trees and I glue them together. And then I can take the metric space quotient, because I view that one of them is describing a metric tree, a geodesic tree. That's the left-right coordinate. Here will be the geodesic tree. And then I just take the just the metric space quotient I get when I glue together 2 points on this tree that are identified with the same point on the upper tree. And when I quotient out by that, I get an honest metric space. And with a lot of work, like all the other people managed to show this metric space is topologically a sphere. Okay, so it's.
Is it possible to take 3 trees instead of 2? Would it still give you like the same result where you can make the whole circle?
3 trees. You know, I'm not really sure what you could do with 3 trees. I don't have any particular reason to think if you did 3 trees, you would get something that was topologically spherical or planar or something like that. I mean, there are various laws for an xt, yt, zt you could use. And you know, you can, obviously, if one of them is a metric space, you can take a metric quotient, you can take topological quotients, those things are well defined. But I don't think you would expect to get something planar. And yeah, I don't know. I don't really have a very interesting answer, I'm afraid, to the question.
Okay, thanks.
All right, so this other approach, these are some pictures from David Gu's gallery, and he did these things jointly with S.T. Yao back in, I think, the 1990s. What they found is they got this data for all these classical works of art. So this is the head of Michelangelos David. And they said, what happens if you take this and conformally map it to the sphere? The Riemann uniformization theorem says you can always conformally map this to something like this. Okay, and what you can see is, you know, the distance function up here will get distorted down here. If I take a small right angle down here, it will get mapped to a small right angle. It's locally angle preserving. It's what conformal means in this context. And if you think about it, this gives a way of representing Michelangelo's David, because I could start by taking the area measure on the head, say here, and pulling it back, and that will induce an area measure downstairs. If I just give you the area measure on this surface, you can recover the length measure and other measures from that. In some sense, this measure I get on here by pulling back the area here, it somehow encodes everything I need to know about this manifold. I mean, not a specific embedding in R3, but it's in terms of as a metric space, for example. So if I want to pick a random surface, I imagine any surface I get, I can pull it back here with the function psi, and I can define an area measure down here by pulling back the area measure upstairs. And what I want to do is define define something where the measure on the surface down here takes the form e to the rho of z dz, where rho is some, say, smooth function. This is just going to be the log of the density of the measure, basically. Okay, so this will be a real function, which means e to this is some positive function. All right. And it is that if you want to choose a random surface, you just have to choose rho at random. If you take rho equals 0, you just get your original surface back, nothing changes. But if you take the velocity of rho to be 0, it turns out that corresponds to rho being harmonic and the surface being what we call flat. So in 0 Gaussian curvature. And the question is, what is the natural measure on rho to choose if you want to choose a random surface? You want it to be sort of a perturbation of a flat metric. It turns out it's natural to take to be what we call the Gaussian free field. And I won't say too much about what that is, but essentially, if you did it on a discrete lattice, I give you a map from, say, a subset of Z2 to the reals, then I could just say the probability of a given phi function is given by e to the minus this sum, or minus a half times the sum of phi x minus phi y all squared over all adjacent pairs x and y. So this is what we call the Dirichlet energy of the function. We're summing the square derivative, square gradient over all edges. And this is a quadratic function, so this is going to be a Gaussian random variable on this space of functions. Maybe you fix some boundary values or something so that it's not an infinite measure. And somehow if you take the scaling limit of this, as you take finer and finer meshes, there's a continuum version. And that's what we call the continuum Gaussian free field. So it's a random surface that it turns out it's a little bit too rough to quite be a function, but it's defined as a random distribution, a random generalized function. It's sort of a version of Brownian motion where you have 2 dimensions of time instead of 1. So it's a map from R2 to R1, generalized function. That's what we call the Gaussian free field. And so due to quantum gravity, you just take your rho to be a gamma times this phi, where phi is some variant of the Gaussian free field. And this kind of goes back to Polyakov in 1980. He invented what we call Liouville theory of gravity, which is basically a way of describing these random surfaces. Although to be fair, if you give this talk to physicists, they will point out that a lot of these ideas go back well before Polyakov. So, sometimes you credit Douglas from the 1930s for coming up with what they call this quadratic action. Hug Krohn in 1971 described this random measure you get by exponentiating the Gaussian free fields. Some of these ideas go back much earlier. The general idea of string theory of trying to sum over surfaces goes back earlier. But here, what I've done is I've taken this measure and I've tried to draw you a picture of the measure over here. And the way I drew the picture is I said, imagine you've got the measure living here, and I try to divide this thing into kind of dyadic squares that have about the same size with respect to this measure. And what I do is I take this box, I divide it into 4, I divide each of those into 4, I divide each of those into 4. But whenever I get to a box where the area, the measure of that box is below some threshold, some delta, then I stop dividing. So eventually I stop dividing everywhere, and I get all of these squares that are about the same size in the sense that they all have area a little bit less than delta. Their dyadic parent had area bigger than delta, they have area less than delta. They're all kind of on the cusp in that sense. And you can see here, this is where you have a lot of things that are relatively empty, very little massive area. This here is, maybe this is Manhattan or Tokyo. And these are the high density regions. These are the low population areas out here. Okay. And as gamma gets larger, the distinction between the rural and the urban grows more pronounced. And you get much empty regions and much denser dense regions, which just sort of makes sense because, you know, if you're multiplying this thing by a bigger constant, that's going to make, when you take e to that, you get greater differences as a factor between different areas. Okay. So here, you know, by the way, this is just the code you would get if you want to draw these pictures. So this produces the Gaussian free field. A very kind of simple code for doing that, just because it's the Fourier transform of something with independent entries, independent Gaussian entries. And then this is, yeah, just that construction. Okay. So now, okay, so recall this Moulin bijection that we had before. And it turns out that there's another natural way to take a picture like this and show you what this map looks like. And it's what we call a Smith embedding. And Smith embedding is a way of somehow, you start by taking two vertices, the upper one and the bottom one, and you put them at the top of a rectangle. And then I take the harmonic function, discrete harmonic function. Basically, I imagine, say, I have an electric flow going from the top to the bottom, with voltage 1 here, voltage 0 at the bottom, and there's current flowing through, and every vertex here gets a voltage. Okay, but then every edge is going to get there's some current which is proportional to the voltage through it. If I ask how much current is there to the left, how much current is there to the right, they will be different. I mean, so 12 currents to the left, not including the edge or including the edge. I can kind of draw, if you like, a square where the vertices are lower voltage, upper voltage, curves to the left, not inclusive, and curves to the left, current to the left if I do include it, the thing. And if you think about it, that gives me a way of identifying every edge with a square. And these are what they call these Smith embeddings. And if you do that Smith embedding for these planar maps, you get pictures that look like this. So let me go back here. Okay, so these are these Smith embeddings. And I have some nice pictures here if you conformally map those to a sphere. I'm gradually kind of shifting the tube up and down. This is just a Mercator projection onto a sphere. But as I shift the tube up and down, I'm showing you kind of like a family of ways of conformally mapping this thing into the sphere. So conformal mapping the sphere is determined by 3 points. If I tell you where 3 points go, in terms of that, and here I'm just showing you the ones that kind of fix the north and the south pole. Here's another family of conformal maps into the sphere, where I'm fixing the north pole and the derivative of the north pole and just swinging the south pole back and forth. And well, here's just rotating around. It turns out, you know, with these kind of 3 operations, you can move around and get any one of these Mobius embeddings. All right, so here's a cylindrical picture of that, projection on a sphere. And so I want to just say that it turns out, and I'm essentially out of time here, so let me just say very quickly, that this LQG sphere is equivalent to a piano sphere. So some of the things we've done in these last few years have shown that all these different approaches are equivalent, these ways of defining this sphere, defining these random surfaces. Now, let me show you one more thing here. Yeah, okay, so this is just our kind of chart. So if you look at this set of all ways of embedding this thing into the sphere, and you choose uniformly among those, there's kind of a natural infinite volume measure on the way of embedding a random surface in a sphere in all possible ways. And then if you look at this embedding in all possible ways, and then we take all possible sizes in all possible ways, this corresponds to what they call Poyakov's measure, which is the basis of what they call a Liouville conformal field theory, this conformal field theory approach. And I can ask you things like, what's the expected product of e to the density at this point times e to the constant times the density at this point times some other thing at this point. And those can be what we call multi-point functions. You can define them from these randomly embedded surfaces. Okay, so that's sort of what conformal field theory is from the random geometry point of view. It's simply just a random surface together with kind of, you embed it according to harm measure, which is an infinite measure. You choose a side from this infinite measure on measure, you get this infinite measure on embedded surfaces. And that's the theory. And this is just, you can't parse any of this, but this is just a chart describing all of the different things that my co-authors and I have been working on over the last 10 years or so in proving that these various different theories are equivalent to each other in different ways. Okay, I will stop.
Are there any questions?
Yes.
Is there a way to do something similar if I say don't care that I get in the end a sphere, but just something two-dimensional of some genus, maybe even infinite? But
Oh yes, yes, definitely. So all of these things have variants for the torus, or if you want to get a higher genus surface.
For a specific surface, but like taking all of them.
Taking all of them together.
Yeah. So that I potentially get something like infinite dimensional, like fractally spongy surface. See what
Yeah, okay. Once you get to this fractally spongy, we start to lose some of our confidence that we have the right way of understanding the continuum structure. Now, up to any finite genus, there's a lot of work on this, and there are a lot of interesting questions even for finite genus. Like I told you, there are 4 ways of defining this. Well, that means there should be 4. We should be able to prove that all 4 of those ways are equivalent for the torus and for the hydrogen. But, or for the torus with n handles or whatever, proving these equivalences for all these different genuses is a work in progress. It's not known how to do that for everything, even though we're sure that they, you can define these things from each one of these perspectives, and they must all be the same thing. But that's, there's some work involved in doing that. But yeah, obviously, when you go to the limit, that's a very natural thing to do when you have infinite genus, foam, crazy surfaces, and I'm not sure, as I say, that we have a right description of the continuum object.
All right, if there are no more questions, thank you again.